alpha n
Hello, sir.
is 0. If this does not happen, we call them linearly
Hello,
independent.
sir.
It is also equivalent to saying that if there is a linear combination, alpha 1 v1 plus alpha 2 v2 plus alpha n vn is 0, implies that each alpha is 0, then is also v1, v2, vn are linearly dependent. This is an equivalent condition, and naturally, in a set of linearly independent vectors, no vector can be 0. We proved that if there are n vectors, namely v1, v2, vn in V, if they are linearly independent, then every element in their linear span has a unique linear combination alpha 1 v1 plus alpha 2 v2 plus alpha n vn that represents the vector v in the linear span, say ls of s. S consists of these vectors v1, v2, vn. We also proved that if there is a set of n vectors in V, then either they are linearly independent or there exists some integer k between 1 and n such that Vk is a linear combination of the preceding vectors. That means Vk is a linear combination of V1, V2, Vk minus 1. Remember what we used in the proof, a simple observation that among all the non-zero scalars, choose the k largest such that alpha k is not 0. That forces that all other higher coefficients, that means alpha k plus 1, alpha k plus 2, and so on, up to alpha n, all of them are 0. And that reduces effectively the linear combination alpha 1 v1 plus alpha 2 v2 plus alpha n vn 0 to the linear combination alpha 1 v1 plus alpha 2 v2 plus alpha k vk 0. And since alpha k is not 0, so is invertible, and you can write vk as a linear combination of v1 v2 vk minus 1, say beta 1 v1 plus beta 2 v2 plus beta k minus 1 vk minus 1, where each beta I is minus alpha k inverse alpha I. So this is what we use to prove that there is some vk which can be written as a linear combination of the preceding ones. This technique can again be used to prove that if v1, v2, vn in V are vectors and W is the linear span, so we can deduce from here. So let us take that V over F be a vector space, and V1, V2, Vn in V have their linear span, and call that, since this is a vector space, so call say W as the linear span of set V1, V2, Vn. Then we can find out a subset of this. So suppose this is S, then there exists a subset T of this S. That means some of these only are required, such that you can rename them required, say again V1, V2, Vk. Let us make a little change. So out of these, say V1, V2, Vn, take up to here, say K. So K is the subspace, which is the linear span of V1, V2, Vk. and also let them let these be linearly independent. Where these V1, V2, Vk are linearly independent. Okay, so once again, so V is a vector space over the field F. V1, V2, Vn are vectors in V, and suppose from these vectors, say V1, V2, Vk, which may be written in that order, are linearly independent, and this we need to we need to change the language in a manner that suppose W is the linear span where V1, V2, Vk are linearly independent, then we can find out a subset. So then there exists a subset, say T of S, say V1, V2, Vk, and then some more. So Vi1, Vi2, and say VIR, such that W is the linear span of T. So T is V1, V2, Vk, Vi1, Vi2, VIR. Okay. So the statement once again is as follows. So V is a vector space over F. V1, V2, Vn are vectors in V. W is their linear span. The linear span of V1, V2, Vn is W. And out of these n vectors, suppose V1, V2, Vk are linearly independent, then we can find out a subset, say T of S, which consists of that is V1, V2, Vk, and a few more, say Vi1, Vi2, VIR if needed, such that T still spans this subspace W. The proof is also using the same technique. So first of all, that it is possible that all of these are linearly independent. That can happen that if k is equal to n. And if that is the case, we don't have to do anything. In that case, S and T will be equal. So the proof, if one has to see, so the first thing is that if V1, V2, Vn, all of them are linearly independent, then in that case, T is same as S, and we are true. Okay, suppose that is not the case. So in that case, what we have is that V1, V2, Vk are linearly independent. So suppose V1, V2, say Vn are linearly independent. Now, out of these V1, V2, and say Vk, these are linearly independent. And we can therefore have a, we can just some Vj is a linear combination of the remaining, and this Vj, this belongs to the linear span of S, implies that this Vj is a linear combination, the linear combination of the vectors from the linear combination of vectors in S, and therefore we can take up the remaining vectors from here. So v1, v2, vk, they are linearly independent, so they cannot be dropped. And then up to vj minus 1, since vj is a linear combination of the other, and therefore vj plus 1 and up to vn. So this also span w, because w is the linear span of all v1, v2, vn, and vj is in the linear combination of the vectors, and therefore vj can be dropped. Now this set has one less has n minus 1 vectors, and these n minus 1 vectors span w. So w is the linear span of this, and this vector j is naturally greater than k. So we have actually dropped one vector here from the set S, and still find that this spans linearly. So what we claim is that this is still equal to W. Now what we know is that from the linearly independent set of vectors, Vj can be replaced by a linear combination of V1, V2, Vj minus 1. And so W is a linear combination of the earlier ones. So that is what we have used. So this way, continuing, what we are continuing is dropping one by one. So we arrive at a subset here, say V1, V2, Vk are retained. So we have dropped Vj from S such that the remaining n minus 1 vectors still span W. And these vectors, because Vj becomes a linear combination of these vectors, and therefore the n minus 1 vectors v1, v2, vj minus 1, vj plus 1, vn still span W. So one vector is dropped, and continuing this way of dropping, we definitely will obtain. So we get a subset v1, v2, vk will remain since they are linearly independent, and some still may be there, vi1, vi2 up to vir, let us say, span all of w, and this is what we need to do. And this process has to stop, because this every time you are dropping one, and you cannot drop when you reach, say, for example, j is equal to k. And when j is equal to k, then all of them becomes linearly independent. So what it says is that if W is a linear span of some vectors, then and suppose V1, V2, Vk are linearly independent, then you can find out a subset retaining V1, V2, Vk that still span W. Now suppose V is a finite dimensional vector space. So next, let us take V to be the vector space over F, be finite dimensional. We defined a vector space V to be finite dimensional over a field F if there exists a finite set of vectors in V whose linear span is V itself. So in case of a finite dimensional vector space, it has a finite set of vectors which span the whole of V. What we can prove is that this set can be taken as the set of linearly independent vectors. So if V over F is a finite dimensional vector space, then it contains a finite set of vectors, say V1, V2, Vn, such that these vectors are linearly independent and the linear span of these vectors V1, Vn is whole of V. So you can recall that for V is finite dimensional, V is finite dimensional. That means V is a linear span of a finite number of vectors. So V is a linear span of V1, V2, say Vm for some Vi's in V. So what we can do is, as just now we had seen, that this is a linear span of these vectors, and out of them, if there are some, say V1, V2, Vk are linearly independent, then we can find out a subset which consists of linearly independent vectors, say V1, V2, Vk and Vi1, Vi2, Vir, which are linearly independent and also span. Further, if V1, V2, Vk out of these are linearly independent, such that then we can have the set V1, Vk, I1, Vi2, Vir is as a subset here V1, V2, Vm, such that V1, V2, K, Vi1, Vi2, Ir are linearly independent and their span is still V over F. So what we can find out is that if V over F is a finite dimensional vector space, then there exists a set say B of finitely many vectors and they're linearly independent, which span all of the vector space we have. And we shall call such a set of vectors in V as a basis. Such a set of vectors in V is called a basis for V over F. So what is a basis for a finite dimensional vector space V over F? Is a set which consists finitely many vectors. These vectors are linearly independent and they span all of the vector space V over F. Now, what we, for example, here, let us take, say, R and the vector space over R. We had seen that the vector, namely the real number 1, is a linearly independent set, and every real number can be written as alpha times 1, where alpha is the scalar, the real number from R. So this becomes a basis. So if vector space is this, and the basis is a basis. For this vector space, in fact, any non-zero real number is a basis. R, where R is a real number and this is not, is a basis. If you take this as R2 over R, then you can take R2 over R consists of the ordered pairs of the form, say, x, y, x and y are in R. And this becomes a vector space with respect to the coordinate wise addition, and scalar multiplication means multiplied each coordinate by the scalar, say alpha. Now B, suppose you take say V1 is equal to 1, 0, V2 is equal to 1. Then this is also is a basis for V is R2 over F is R here. Since this consists of finitely many vectors, namely two vectors V1 and V2, and every vector is a linear combination of these two vectors, These are linearly independent also, and therefore this is a basis. Now, if you take this as say R3 over R or Rn over R for that matter, so this consists of n tuples, say alpha 1, alpha 2, alpha n. Each alpha is from R, becomes a vector space with respect to the coordinate wise addition, and scalar multiplication means each coordinate is multiplied by the scalar, say alpha. And for this, let us take V1 as 1, 0, 0 and all zeros. V2 as the n tuple whose first entry is second is 1 and all other remaining are 0. Vn is 0, 0 and then 0 and the last is this. Is a basis. For these vectors are linearly dependent. For V1, V2, Vn are linearly independent and they span V also. As every vector V, say this is x1, x2, xn, can be written as x1 V1 plus x2 V2 and so on xn V1. Is also a basis. Now such a basis, so we can now replace this R by any arbitrary field. So let us take V to be Fn over F, where F is a field. So this is a vector space over F. Once again, the addition is coordinate wise and multiplication by alpha is the n tuple where each coordinate is multiplied by alpha. Now for this, if you take B to be, say V1 is 1 because F is a field, so it always has identity with respect to multiplication 0. V2 is 0, 1 and 0 and so on. Vn is 0, 0 and this is 0, 1. Now is a basis for V over F. The basis of this form, they are called standard basis. Basis of the form, so B is called standard basis for V over F. Basis is not unique. For a finite dimensional vector space, is not unique. For example, when you take say V as R2 R, V1 we had taken this as V1 as 1 0 and V2 as 0 1, the standard basis. And you can also take V2 as say 1 0, say this is U1, U2 as say 1 1 is also a basis. So basis is not unique, but then only the basis B1 is called the standard basis. There may be other basis, say B3. So you can take W1, say this is 1, 1, and W2 you can take as, say, 2, 3. There is also basis. You can prove that W1, W2 are linearly independent, and also you can prove that W1 and W2 span full of vector space V over F. Okay, so what we have is so far for a finite dimensional vector space that there is a basis. There is a basis means so it consists of finitely many vectors which are linearly independent, and they do span the whole of the vector space. While giving examples of different bases for say R2 over R, we have found that both had the same number of elements. Each of these had two vectors only. We can also have other examples. So say if you take V to be fx, this is the set here of polynomials, then you can also have here a vector space. This is a vector space over F, set of polynomials. The summation of two polynomials is defined to be a polynomial where the coefficient of x power I is some ai plus bi, where ai is the coefficient in fx and bi is the coefficient of x power I in the polynomial gx. And alpha times fx means so each coefficient of the x power I is alpha times ai. That means each coefficient is multiplied by I. And so if you take say Vn for example is the set of all polynomials of degree say less or equal to n. In that case this is a polynomial here in fx. And the degree of the polynomial fx is at most n. Then this Vn is a vector space, and this is a finite dimensional vector space. And one basis which is straightforward can be seen as 1x and x power n. This basis is called the standard basis. Is a basis for Vn over f. B is called standard basis for Vn over f. There are other bases for Vn over f. For example, you can take say B1. The vectors are say 1 plus x, 1 plus square, and 1 plus x power n. Call say this is B2 if you call this as B1. And you can also take 2, say for example 1, 1 plus x, 1 plus x square, and like that 1 plus x plus n so on, x power n. So here in B2 the elements are 1 plus x, 1 plus x plus x square, 1 plus cube, and the last is 1 plus x plus x square plus x cube n. So these are also bases. You can prove that B2, B3 are also bases. Are also bases for this. However, B1 is called the standard. Here also, what you can observe is that each of B1, B2, B3 have the same number of elements, namely n plus 1 number of elements. So what appears is that if V is a finite dimensional vector space, in that case, any two bases will have the same number of elements. So this is what we want to prove. So before that, we prove this observation. So let us take here, say V over F is a vector space. V a vector space. And suppose this is finite dimensional. And we have a basis. And let us take V, say V1, V2, Vn, a basis for V over F. So what does it mean? That so that means V1, V2, Vn in V are linearly independent, and the linear span of these vectors is whole of the vector space V. Now, if W1, W2, and let us say Wm in V are linear independent over F, then what we prove is that this M cannot exceed N. Now for this, what we see is that because V is spanned by V1, V2, Vn, and therefore every vector in V is in the linear span of V1, V2, Vn. In particular, each Wi also is a linear combination of V1, V2, Vn. Now, V is the linear span of V, and this Wm is a vector in V. Therefore, Wm is also in the linear span of V. That means this Wm is a linear combination of V1, V2, V. So Wm is a linear combination of Wm is a linear combination of V1, V2, Vn. That means there is a linear combination. Say alpha 1 V1, alpha 2 V2 plus alpha n Vn plus say alpha n Wm is equal to 0. And that makes that if you take Wm also, together with Wm, the vectors are linearly dependent. So the vectors Wm, V1, V2, n are linearly dependent. Also they span V, V1, V2, Vn. Already span V, and therefore there should exist some proper subset. Hence, there, hence there exists a proper subset of these vectors. That means Wm, V1, V2, Vn. Say Wm and then Vi1, Vi2, VIR or VIK, whatever you want. Where this K is definitely less or equal to n minus 1. And they still span. Spanning the whole of the vector space V over F. And are linearly independent. This and these vectors are also linearly independent. That means this also is a basis. So what we have got is, if V1, V2, Vn is a basis, then we have pushed one Wm, and in trade-off we have thrown away some Vn. So if you repeat this process, so we obtain like that every time we shall push one W. So the next stage will be this. The next we get a basis, and this new basis has vectors like this Wm minus 1 Wm, and then Vi1, Vi2, and say Vik. So every time we are pushing one W and throwing out at least one Vn. So we can find out a basis, let us say Wm minus 1 Wm, and I we have used there, so let us use here J, okay, like that. And let's say this is Vj S, Vjs, and this S cannot exceed n. So this is a new basis here that we have obtained. Now continuing this process one by one, inserting W's and throwing away vectors. So what we get is a basis. So like that we get a basis, W2, W3, and let's say Wm here. And some V's will be there, V alpha, V beta, and so on. For V over F. Now what we know is that W1, W2, Wm, they are linearly independent. So W1 cannot be a linear combination of remaining ones. So since W1, W2, Wm are linearly independent, W1 cannot be in the linear combination of the remaining ones, that means W2, Wm. This cannot be a linear combination of this. And therefore, this should have at least this basis, this should have, because we cannot push W1 also inside this. So there has to be some V alpha from the original ones. So this should have some VIs, some VI, because if there is no VI, in that case, this will become W1, W2, and Wm only, making this because they are the linear span. So making W1 as a linear combination of these W2, W. So that cannot happen. So some VI has to be there. So in this process, what we have done is that we have pushed into m minus 1 number of W's, namely W2, W3, Wm. And every time at least one V has been thrown out. And this gives us that m minus 1 has to be less or equal to n minus 1. And that will mean that m is less or equal to n. So what we have is that if there is a basis and there is a set of linearly independent vectors, say W1, W2, Wm, then m cannot exceed n. That means the number of linearly independent vectors in a finite dimensional vector space, say V or F, and if a basis has n number of elements, number of linearly independent vectors will be at most n. And naturally now you can prove that any two bases has any two bases for a finite dimensional vector space have same number of elements. Naturally, for example, if Fn is a vector space over F, Fn is also a vector space over F, and Fn and Fm are isomorphic, you can prove in that case and same. Now, once it has same number of elements, this number becomes unique, and this number of vectors in a basis for vector space V or F is called dimension of the vector space V. So quickly we can see that so the dimension, so this Fn over F is a vector space here and is a finite dimensional vector space. and the dimension of V over F is n. So that particular gives that the dimension of R2 over R is 2, and of R3 over R is 3, and the dimension of therefore Vn over F is n plus 1, as the standard basis consists of n plus 1 vectors. What are these vectors? 1, x, x square, x cube, and so on, x power n. Any other basis also has the same number of elements, namely n plus 1. Other two bases, say B2, 1, 1 plus x, 1 plus x square, and last element, 1 plus x power n. So that also is the case. You can deduce from here for a finite dimensional vector space. If you have some linearly independent vectors, say v1, v2, vm, then you can add it to this list such that you get a basis for this. So this I'm not proving, you can prove that. So if V over F is a finite dimensional vector space over F, and if say V1, V2, say Vm are linearly independent vectors in V, then there exist vectors, say Vm plus 1, Vm plus 2, and say Vm plus R in V, such that V1, V2, M, Vm plus 1 R is a basis for vector space V over F. We shall wind up here on Friday and have some more deductions about the finite dimensional vector space. Okay, so thank you very much.